Hello viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about efficient computer, their Silicon E1, worst name ever. So let's dive deep into it. So what exactly is the problem right now? Problem is that we are deploying compute everywhere and in more and more places. Plus it's accelerating, meaning we used to have 1000 computers in space, now we have 10,000 computers in space. So numbers are expanding exponentially. So yeah, we are reaching a bottleneck at this point in time, and the bottleneck is energy. At this point in time, well, the limiting factor is not the silicon or the technology, it's just that how much energy these things consume. So that's the whole point. And there are certain scenario where it is so energy constrained, like satellites or your smartwatches or basically any sort of embedded devices, where it's like every single joule is counted. You have to be efficient. You do not have the luxury of like drain as much power as you want. We have reached that point. So at this current juncture, as in year 2025, the people who are going to be making money in future are the people who are going to figure out how to reduce energy requirement of compute. Same amount of compute, if not more amount of compute, has to be done in future, but it has to be done on lower and lower power budget. So we have reached a point like computers have grown, like we got this, compute, good, got this. It's just that the power draw has to like calm down. We cannot go from like, oh, the early days, like computers were consuming 200 to 500 watts of power. Now it's 8 kilowatt of power draw. No, there is a limit. So same thing, we are reaching that. Like for example, your electric vehicle, you're like, okay, I have this electric vehicle, I have so much power, I can just run a heavy compute to do self-driving. Yeah, here's the deal. Your electric car can go, some of them, up to 3 to 5 kilometers per unit of electricity, and similar amount of electricity would be consumed for 1 hour of air conditioning. So not that expensive in terms of energy wise in normal scenarios. But here's the deal, what if your self-driving computer is not energy efficient? Turns out that puppy is consuming like 10-20 kilowatts, as in like a unit of electricity. At that point in time, yeah, it's not valid anymore. So that's why this is how we used to try like self-driving in 90s, or like lab grade experiment and all that. So fundamentally, power limitation applies to everything. This is what we are struggling against right this point. Like if you have a CubeSat, you have a CubeSat. You do not have like, what if I have 10 kilowatts of power? No, what you have, that's what you have, figure it out. So that's the fundamental problem of modern time. It does not matter whether you're talking about self-driving cars, satellites, smartwatch, or AI data center. Even in those centers, like it's not logical to go to a national electrical state board and it's like, yo, man, give me 10 gigawatt. They're like, bitch slap you. They're like, bro, build your own power plant. That is that kind of power we are talking about. So that's the fundamental limitation. So what are our current solutions? Well, the era right now we are utilizing and the profits that we are yielding, it's from VLSI. Now this VLSI is basically very large scale integration. Basically we started with these sort of silicon, and if you want to look into the early days, look into Apollo mission, the first actual utilization of integrated circuit. So we started with that, but again, people very soon realized that only genius people could actually build it, because they had to understand the whole pipeline, basically how the silicon reacts, how this reacts, how the etching process works, how do you physically make the gates and AND gates and OR gate, everything you had to physically know. So we reached a upper limit, and it's happened as late as 1980s, where like, yeah, we reached upper limit. You can't go, like, you can't build an industry if it requires once in a million genius. So people were like, okay, what if I create something clever? So some people got together, they created this VLSI. It's almost like a language. So people came up with the idea, is like, what if we standardize this? Basically, instead of having like 4 nanometers, that time it was 200, 800 nanometers kind of thing, or some early days were like just millimeters. It's like, okay, lambda. This is the lambda, and you design it, and they created a language, and more people poured their intelligence into it. So over time, that became a ethos. That ethos allowed this to happen. Basically, going from this to this happened because of that ethos. That is VLSI. That's why now you can practically talk with someone and be like, okay, how much transistor this puppy has? They're like, it has 1 billion transistor. Like, damn. And then it's like, this has 1 trillion transistor. I'm not even joking. And then there is a like silicon wafer CPUs. Those have million cores. So fundamentally, we went all out simply because of VLSI growth. A lot of people put their intelligence into the language evolved. So it became the bridge between what you're thinking versus what can be manufactured and all of those things. So it grew. Right now, the biggest Beneficiary is what we call common computer, which is CISC based or RISC based, and the world runs on it. Now here's the problem with that: that designs are ancient. That design, like basically the actual silicon design, is ancient. It's simply to do any task. It's almost like a miniature computer inside your computer core, where it takes data from the cache, takes the data, crunches the data, dumps the data into cache, and then do it again and again. So it's, even to do a simple operation, it is dumping data in and out of cache way too much. And how much that is? Well, here's the deal. This is where it gets horrifying, is that compute power required by the joules. Basically, if you have 10 joule of energy, how much oomph you can do, how much crunching you can do. When you're talking about the CPU part, it's like, bro, we got this. We got this. We can do multiple operation in few joules. Good, awesome. Yeah, but reading and writing from the cache, that consumes more. Like, they are fundamentally being limited by the read and write operation of the cache. And because it's happening on every clock cycle, and it's like really deep in, it's like it is what has to be, that is fundamentally limiting and burning energy. It's almost exactly the same thing that I was talking about, NVIDIA's jump to optical interconnect, simply because the nodes were very efficient, but the communication between the nodes were taking a lot of energy. So same thing happens inside the silicon also. The silicon that is doing the, it's awesome, it's good, we got this. It's just that, oh yeah, writing to L1 cache and reading from it, writing to it, reading from it, and L3 cache, God help you. So that creates a fundamental bottleneck in the silicon itself. How low latency you can do, it depends how quickly you can read and write. How much efficient it depends how much it read and write takes. So compute is surprisingly efficient on a silicon level. It's just that transmitting data from here to here, heavy. So you're like, okay, what alternatives do we have? Well, we have certain alternatives like field programmable gate arrays. Now this puppy is a silicon that you can tune and adjust. It's like a blocks that you can align. It's a Lego that you can electrically program. It works, it's very good, but this puppy is expensive AF, and the best FPGA still can't compute with the, like, high-end CPU and all that. But it, for a dedicated task, FPGA does have benefits, but it's expensive AF and complex programming. Programming is brutal, meaning there are countable people on the planet that can deal with quality FPGA computation. And then you're like, okay, how do we run the world then? Well, we run the world on ASICs, what we call application specific integrated circuit. Like, okay, so why don't we use that for everything? Well, it's hyper expensive. It makes FPGA look cheap. Now, the only reason ASICs can be utilized is because at bulk scale, it makes more sense. For example, your Nikon is not gonna go to NVIDIA or ARM and all that, and they're like, okay, can you make a imaging chip for us? It's gonna be too goddamn expensive. It will be flexible but expensive AF. So they're like, okay, we're gonna sell at least few million of these puppies. So they're gonna make their own processor. Let's say call it X-Speed processor. Same will happen with Sony. Sony is like, yo, we can go to this and all that, or we can build our own. They can build their own. We call it Bionics. And Canon, I keep forgetting, Digix. Yeah, Canon calls it Digix. So those are application specific. They are very energy efficient. That's the best part about them. The amount of energy they consume to do the task, it's least, but they are very locked down and idiotically expensive. They are not general purpose CPUs. So when you are talking about general purpose CPU, ASICs do not even come into the picture. ASICs are like, once you have figured out what you want to do, like a GPU or NPU, then you can make into ASICs. So each systems have their own pros and cons, and current market is dominated by what we call simple general purpose computer. That's it. Like if your power stabilizer, your air condition, all of them have silicon. All of them have generally ARM Cortex into it. Generally, not the latest and greatest ARM Cortex that you see in your smartphone, but embedded ARM Cortex, so to say. But they are not efficient on a silicon level. They are not that efficient, meaning if you are trying to make your smartwatch very energy efficient, removing the radio consumption and display consumption, after that you will reach silicon consumption, energy consumption. That cannot be changed because it's stuck fundamentally on a core level. Like it can't be tampered. It's not like, oh, what if I make it better? Nah, you can't. Like it's a physics level. Like there is an inherent limitation. You can optimize the software, it will only go so far. So that we have reached this point. Like this technology is all the tools that we have used. It's awesome. But now we are reaching, it's like, we gotta do better, man. It's like, we can't grow beyond this point. Basically, your AI girlfriend requires a bit more efficiency. This puppy runs on like 20 to 100 watts. Your AI girlfriend has to run on lower power than that. Like she can't run on 5 kilowatts. Like she will be too hot. So we come to the worst naming company in the history, which is Efficient Computer. Who the heck came up with that name? But somebody did. And this company was founded in 2023 by Brandon Lucia, this individual. Now, here's the deal. This sort of thing is grown company rather than like a made company. Basically, the roots of this was Carnegie Mellon University from Pittsburgh, Pennsylvania, America. Basically, universities, some smart people got together, they had a project and people got into it and they were like, hey, this is something useful, this can grow. So they spun it into a company. It has happened, it's a normal thing. And you want, like if you have a good, healthy university, you want this sort of thing to be regular occurrence. Because again, that gives them a early starting period, a lot of data checking, a lot of verification, and then tada, there is a company which could grow into multi-billion-dollar company. So they started that. Now, right now, they are very specific, very precise. This is a good thing. Even though their design inherently has no limitation, it can become the next big CPU. They are not targeting that. They are targeting what we call power constraint IC market, meaning when you are looking into the power constraint market, every joule of energy counts, meaning you literally have to calculate that. It's like you are making a remote for your, let's say, LG. Those things can't consume a lot of power because again, if it does too much power consumption, it's not going to be efficient. Customer's going to have a bad experience. And again, smartwatch. And God help you if you're dealing with satellite. At that point in time, it's nah, bro. Every microwatt matters. Self-driving algorithms, ooh, everything matters. Like I do not wear watch anymore simply because the Timex watches, they are horrendously bad. Like compared to Casio, that I haven't swapped the original battery that has crossed 10 years versus these puppy, they were consuming almost 2 batteries per year. So, sorry, 1 battery per year. So fundamentally, there are scenarios where you have what we call power constraint integrated circuits. So fundamentally, they are targeting that. They are directly firing missiles at ARM Cortex M0. Like, isn't that ancient? Yes, it's ancient, from 2009 ancient. But here's still, that's still in use. Many things have it installed. Now, many times we take orgasm over like, 3 nanometer, 2 nanometer, 1.2 angstrom. But those are not the core of human world. Like most of human world runs on like freaking 22 nanometer node or even 60 nanometer node. I'm not even joking. Like your solar inverter is not running on 2 nanometer. Ain't nobody got time to waste on that. So fundamentally, they are targeting on those sort of environment. So E0 prototype was made with 22 nanometers FDX process, which again, reasonable, logical. If you want to scale it up, more than good enough. Nobody's going to complain to you. It's like, oh, why 22 nanometer? Does not matter. At energy sensitive system, you want to make it not very small because again, heat generation becomes an issue. And again, you must have seen like NVIDIA generally tries to make the die itself huge because otherwise you can't transfer the heat. So like, okay, what if we packed a lot of it? Yeah, you pack heat also. So fundamentally, that 22 nanometer, shut up, take money. It's cheap, easy, scale up, go YOLO. So Electron E1, basically this puppy, was released in July 24, 2025. So very fresh out of the box, so to say. So this is Efficient Computer. Who came up with the name? 4 people. None of them had a brain. Whereas like, hey, let's name it something that people can actually read. Efficient Computer. So let's understand the design of it, what they are doing different. Well, it's not one massive core because if you really try to understand what's going inside a silicon, it's actually just a miniature computer which has everything like data comes in, data gets passed, data gets stored from the memory, then it goes there, then it branch prediction, all that. It's literally a miniature computer. So, and it basically means it has a lot of data putting and pulling from memory every step. So that is not acceptable. Again, inherent energy limitation. So E1 fabric architecture, this puppy fabric architecture, it's basically micro nodes. Now let me be clear, node is not same as core and this is micro node. So this is a neutered system. It's basically the die budget, as in like how many transistors they have. It's very tiny. It's not a full core that is like, doing a lot of things. It's a very simple, very dumbed down. It's like I do addition, the end. I do subtraction, the end. I do multiplication, the end. Now like, wait a minute. Wouldn't that mean you have to have a lot of nodes? Yes. There are a lot of variety of nodes. That's why they generally use different colors. And the key part is data moves and gets processed and moves to next step processing without memory detour. Meaning if a packet of data comes from here and it's like, okay, do this A, B, C, D, they'll go tweet, 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 tweet. And once it's done, then it dumps out. The end. There is no detour like, okay, go there, clock cycle, sync data, clock cycle, sync data. No. Go do as much cycling as you need inside the fabric. And once you come out of the fabric, you're done. So fundamentally, it does not have memory detour, meaning on the core level, like what's happening on the silicon, it gives you two things. First, it gives you low power design because the nodes that are not being pinged, they're floating. They're like, bro, we do not care. They're just off. They do not care. They're not designed to care. So very serious energy savings, because it's off means off. The nodes are off. Basically, the silicons are only coming online when they're actually doing crunching. If they're not doing crunching, they're not wasting time. It's not basically the whole clock cycle and all that. So it's a very clock independent, rudimentarily speaking. And it has low latency architecture because data goes in, does the whole thing, and then comes out. This puppy is low latency. How does that matter? Here's the deal. Work with audio engineers. Everything in audio is super duper hyper latency sensitive. This puppy is so fast, it's like, bruh, relax. We got this. So that does matter. And again, this is on a fundamental level. So low power design, meaning even if their Mark 1 product is not whoa, it will become whoa because the core is that good. And nodes are small cores, let that be very clear. They are not complete cores. They are very small, one fixed operation. So they have variety of nodes. One nodes would be, let's say, decoding, one would be encoding, one could be like writing data to this or pinging data to that or interrupt functions. It would be very simplified. Now you're like, okay, how the hell do you code something like that? Because again, inherently your instruction has to go out of cache and be like, okay, do, and then come back. It's like, that's a complicated instruction. Yes, it is. So they have their own EFFCC compiler. Now the compiler is the key part. Is they are very smart. They know for a fact that if they ask somebody is like, hey, learn a new language, new machine language, nobody's going to do that. So the idea is you're going to code in normal quote unquote C, and that C would be converted via compiler. Compiler is going to do the heavy lifting. It's like, how do I package this instruction in a machine language so data follows the pathway that needs to be followed? Basically, the compiler will do the conversion for you. You do not have to do that. And if done correctly, then you're going to have super duper energy efficient operation and very ludicrously low efficient, what we call latency sensitive system. So that's all. But compiler is the black magic part for them. Like if the compiler is good, they're good because the core is solid. What they are trying to do, it's almost like a code that knows what it has to do. And it's hardware that accepts it. It's not a generic hardware. It's almost like go through this path if you need to do this, go through that path if you need to do this. And it's not creating like, load everything, do as fast as possible. No. It's like, if you need to go through a lot of these, go through a lot of this. If you don't need to, don't. So fundamentally, really clever. Everything about this is clever, assuming the basically compiler is actually works. Because again, I have to say, whoever designed the compiler, they're high, like intelligence high, kind of high. But again, that's the design of it. Surface level, don't dive too deep into it. I can't understand it. So what can we expect in the future? Now, this is what we call bowls, because this is a high risk, high reward scenario. There is no middle ground in this. Meaning this company will succeed, and we're gonna look into it in the future, 10 years from now. If they succeed, it's like how this company became the next big thing. And because again, they're going all out. They're touching things that nobody else dared to touch. Like look into risk. What it is, it's basically going backwards to where we used to be. Like Cisco was a what you call bad detour, so to say. People were making risk. ARM is risk, and they're like, okay, let's make a RISC-V. It's basically taking the same ethos, same ecosystem, and making it open source. This is like, no, what if we change the core ethos of computation itself? So the high risk, high reward. Let that be very clear. This is bowls. This is basically the same bowls Jensen Huang had in 1990s. This is bowlsy. So it could work, or it could just go. So computer world is very risk averse. Why is that? Well, right now that's where the money is. People don't risk things when it's a growing industry. People risk, when it's a saturated industry. Right now, if your age is 30 years old, you must have seen big oil. People used to fearmonger about like oil companies in 1990s and 2010s till 2010, and now it's like big data, because again the crown has shifted. So right now, compute world is very risk averse. Everybody wants to make hardware, but they want to be like very guaranteed, so to say. So they're very risk averse. So how would you break into that environment? Well, you have to be significantly better, meaning as they are claiming 100x better performance per watt. Now, can it be actually 100%? I don't think on a device level. I don't think that is possible, because let's just say you made a smartwatch that is utilizing this core, and core is that efficient. Would that save your battery life that much? No. Why not? Well, most of the energy is consumed by the display. and then radio. Those things will still consume the same amount of energy. That's law of physics level. You can't tamper with it. So CPU will only give you, let's say, best case scenario. You go from 2 days of battery life to 4-day battery life. But again, in satellite, people will be like, shut up, take money. Shut up, take money. So they have to be significantly better. Are they better? I hope so. But how much better? That has to be tested over the design life cycle. We cannot know that in day one. It has to, like, things have to be designed, things have to be made, manufactured, sold to consumer. Consumer have to go through years of it, and then we're gonna know, oh, now we are reaching. Because again, I do expect the compiler to have go through multiple generation where they're like, no, this was good, now it's good. Like how PlayStation 3, the early launch titles looked like, well, PS2 like, and at the end of PS3, it's like same hardware looked like, whoa, it's the same hardware. It's the same thing. It takes time. And again, because the black magic they require for compiler, I do expect that kind of thing to happen. So fundamentally, they have to be very better in order for somebody to take a gamble on it. And again, core is sound. What they are trying to do is logical. It's almost like, hey, we cool, we got this, but this is 1970s design, man. Let's try something new. So that is a good approach, and they are actually working in such a way where it's like, no, we have the experience. We know what risk is, what risk is. Inherently, they are the same thing. It's like same thing as in like the instruction architecture is the same. So they're like, hey, what if we change that? Like how the execution happens itself. So that's good. Assuming the compilers for this could be big. And this IP has fundamental advantage. But again, it's up to the people will risk it or not, and time will tell. Now, let that be clear. There is a probability, gray probability, meaning either this company becomes the next big thing or just fades out. But there is a gray probability. Basically, missile companies would be like, hey, you have all the in-house IP. How about we just... Because what is more energy sensitive and latency sensitive than a missile guidance package? And again, I'm not joking. Somebody is smoking in America and they're like, hey, what if we had handshakes for missile? And if you don't understand what that means, that simply means they want something else to launch the missile and something else to guide it. It's just like, launch missile there. It's like, sir, we do not have target data. It's like, just launch, nah. Like a destroyer will have, and the fighter jet mid-air will like, yo, come here, come go there. They're doing with missiles, traveling at Mach 5 plus. What are you smoking? What is the latency? It's almost like the latency that I've seen into German anti-drone system where they have like a big pew-pew cannon, auto cannon, and this cannon have a fuse in the projectile head that is programmed while it's being fired. What the hell? So I can easily see some weapons company looking into this. It's like, wait a minute, you are telling me on a fundamental you can reduce latency? Sir, just don't worry about money, sir. Just come in. Just come in. So there is a probability there. So this was my presentation on basically the worst named company in history, Efficient Computer. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.